coming to the topic of today, we are going to talk about structural information as the basis in a BIM environment where we believe that we use the structural information as one of the primary source of a project when we can gain more insight. And currently, as you know, the structural engineering profession and structural engineers in general are a little bit lagging behind in the adoption of the BIM models and BIM integration to the other disciplines. So I'm going to emphasize today the significance of using the structural information as the base for the buildings and other structures. So let me start with this an obvious point. If you look at the slide, you can see that these are the desks arranged in a building with its interior, and you can see that they're kind of floating in the air because there's nothing there to support them. So the interior designer's work is literally in the air at this time. Similarly, if you look at that is the firefighting system in a building, and once again, it seems to be floating in the air, and it has to perform an important function, but currently it doesn't seem to stand on itself. Then we have the HVAC, the MEP, and the heating and ventilation ducts. Once again, they are very important, or whether it's functioning, and they, the energy on that stuff. But once again, they seem to be just hanging in the air or floating in the air. And then we look at the architectural components. For example, the partition walls, the flooring, the railing, the windows, and they are not reaching the ground. They again are defying the gravity. So what is it that is missing that will make this complete? Structure. So as soon as you have the structure, we can see that the structure is actually taking or sitting on the ground. It's grounding everything in reality. So once we have the structure built, then we can break in all of these disciplines and their components and add to the structure. And we can have the interior, we can have the fire systems and MEP and the architecture components attached to the structure's core, and we can have one really complete. So this is quite obvious, I'm sure, but to make the point, you can see that none of the other disciplines' work can actually become a reality or useful until the structure is well built and it is tightly integrated with these work. So the obvious point that we can make from here is that we need to integrate all the disciplines, and especially ultimately with the structure, because that gets built first. So on that basis, we can see now that all these disciplines can do their work more or less independently. They can plan, they think of their requirements, and they can develop the systems independently based on their design forwards and their own final outcome. But they have to communicate with each other because one depends on the other. So information exchange has to be done. Collaboration has to be done. It's essential. I think most of you who have attended any coordination meeting in a project, you know that we have 10, 15, 20 professionals sitting around the table in an important project, and then discussing how their work can be integrated or can be connected to each other. And then structure, of course, needs all that information. I personally have attended several meetings when we are always everybody's fighting for the core or core lift for the building and trying to economize, and then, debating on where to cut or where to add openings and so on. So we all know how this goes on. So this kind of collaboration is very helpful, although independent design is possible, but ultimately it has to be coordinated. So construction, on the other hand, is sequential. That means we can't build the interior first. Structure has to be built first. We can prepare something, but the actual physical site work has to wait until the structure is completed or partially completed. So, which means that this sequence is essential. The structure does come first in terms of how the buildings or other structures are built. So, keeping that in mind, we can now look at the entire life cycle of a typical building and see where does this information flow is essential and how the structure information fits in. This is kind of a linear life cycle flow of a typical building, and as you can see, there are like 24 or 25 steps there, starting from the project initiation, location selection, initial feasibility, initial financing, site acquisition, then consultants engagement, then on-site design, site structure, all the way going to the detailed design, to contractor selection, construction permits, groundbreaking, ceremony, and construction management, and so on, until the structure is more on the immediate and it is end of life and we have to decommission it. In fact, I remember one of the projects that we doing, just the groundbreaking ceremony, they built a whole building, temporary building, to launch the main building, which they just want to demolish the next day because they wanted a huge event with several celebrities joining that. So this life cycle is quite common in most of the structure and has so many stakeholders, so many phases in there. And if you expand that, we can go into more details and see how many sub-tasks they have to perform, sub-consultants have to come in, and so on. So it's a complex, the system that starts with the concept of the client until the building is occupied and finally decommissioned. Now, the structure information can help in these areas, these parts of these phases of the overall life cycle. But in reality, structural engineers are engaged much later in the process, and that's why their information or their input does not get into the other phases of the life cycle because they are normally engaged at a much later stage. But what we are saying is that if we have a structural information somehow developed earlier, it can benefit the whole life cycle management in a much better way. So this is not all the places where the structural engineers get involved. Some buildings, but some projects more, some projects less, some projects even much less, just from the design, and after that, they're not involved. In some, they go to the site. In some, they have the more interactive design. So it depends on the project and the team and the nature of the project and how it is executed, turnkey or competition based or whatever. So this is the way of structural engineering can play a role. We all know about the BIM and how it is changing the workflow, how it is facilitating the interaction, it is facilitating collaboration. I don't think anybody is not familiar with these messages of the BIM and its adoption. And this is a slide from Autodesk, which obviously is one of the key proponent of the system. And we can see that it has conceptual design, detailed design, analysis, documentation. Part of that, most of the disciplines are there. And finally, demolishing, decommissioning, and then renovation, and then so on. So it more or less covers many of the phases that we saw in the overall life cycle. Now, I want to come to something important here, which is the information. Information these days, as we know, is so diverse in terms of type of information and where it is stored and how it is stored and how it is presented. So if you just take the information and look at the mind map, you can see the information is on internet, on models, of drawings, of media, videos, images, documentation, CRM, SQL, all that, Excel, what's the Excel, and so on. So we have thousands of files, different format, different models, different places, all scattered. People are thinking some piece of in front of a structure, that's information. There's a crack, somebody notes it, they notice it, and report to the building and maintenance people, that's information. So information is being constantly generated right from the beginning until the end of the structure, especially with these days, which everybody has access to publishing the information and also to acquiring the information. So if that is the case, then how can we create a context for that information that it becomes useful? So if we take all that information, for example, about what being on this building and attached everything to that beam, then we have a physical connection of the information to the physical BIM, and we can store all that in the references or whatever system, so that when we know, with this beam, this is what has been done with this beam right from the beginning until now. About painting, about cracks, about its visibility, or somebody draws something on it, all the information can then be referenced back into BIM model and into BIM system, and it refers like that. So this is how the information, all kind of information, can be sort of laid back to the building or to the search. So structured information, if you connect it to everything, it will ensure that we have all the work-building elements properly designed. We can optimize the structure, optimize the use of the material, comply with the building standards, and then we can have a lifecycle maintenance and management, and disease planning. So many more things can be done if this information is properly stored and managed. One of the key issues, I think, is that when we try to promote the BIMs, we cannot find who is the person who will be most interested to store and maintain this information. And I'll come back to this in a minute. So, but the research instrument, the structural information has two ways. First, it needs to get information from the architects to plan and size things, and then the architects need to have the information of the sizing for clearances and all of that stuff. So it's a two-way communication. One depends on the other. Same thing happens with MEP, the opening locations, because especially I know from experience that MEP, most of the time they would like have an opening next to the column. And structural engineers, we don't want it there into the matching shear area. So it's always a point of contention. How do we manage openings in the slab, for example? So those kind of information management is very important, and coordination is very important, and this effect of one CN on the other is very important. Similarity material and the other disciplines. So the information flow between structures and other disciplines is often two-way. Structure needs to support the facilities, and those facilities need to know what the structure looks like after it has been designed or sized up, so that they can replan it. Like, for example, I can give you an extreme example. In one of the buildings that we were doing, and then the meeting, I saw, the interior designer told the client something, and then the client said, "Can you take this corner, which is going up on the 9th floor, move it back by a meter, and then move it up to 17th floor and move it back in the front," because the interior designer wanted the column not to be visible on the window. So this kind of requirements can alter the whole structural system. But that can only be possible when such systems are developed together. This is an expanded model for lifecycle management. It goes much beyond what I presented earlier, and it is mostly from the structural engineer's point of view or eye. And so it starts with a IFC data, for example. We have a charging model, post-analysis, structural analysis model, design model, and then compliance model with the code, so we can have the permits issue. Then we can go to the detail model, and then we can have the construction model, BOQ and cost model, sustainability model, logistics model for bringing the material in, detailed financial modeling for the final costing, and the EIA model for the environmental studies. Then go to has-been model after the description is complete. Then we can have LiDAR scans or drone scans or images to supplement that construction, as-built construction or changes being done there. And then we have the digital twin, which can take the information and create a complete digital twin for that. Then security model for managing the security of the building, facility management model, resilience model, structural health quality model, performance-based design model, retrofit model, IoT sensor model. So you can see now that suddenly we have the opportunity to handle a lot more if the structural information is properly stored and is all available throughout the life cycle, through to the all the disciplines, and it can be combined together. So this is a major sort of expansion or extension of the BIM that can add more value to the structure, especially from the structural performance and resilience point of view. So that brings us to the point that structural detailing could be the starting point of the workflow, so that the structural detailing is actually what is built. I often tell my colleagues that when they're constructing something that's a column on the side, the workers or the people over there, they just have one information, size of the column, number of bars, and their location. They don't know, and probably they don't care whether we use ETABS, we use BIM, we use whatever software to arrive at that. What will be constructed is what we provide them on the site, and that's all that in the end really will control the construction. So if that information is already available somehow at any stage, then we have this good starting point. So based on that idea, let's look at the traditional workflow for design process or structural design, for example. Typically, this is what we teach, and we have been thinking about that. Okay, we have architectural functional plans, we have the structural system, we have trial members, we do the modeling, we do the analysis, we then call this conceptual design, we call this one as modeling and analysis, we can involve that like listing design, final design, output, drawing design, and if it doesn't satisfy, then we revise it if it is not working. So this is the traditional way to do that. But with all of this digital information and parametric modeling and BIM, we could have an alternate way of doing the same thing with an alternate workflow. So this is the alternate workflow. That means detailing is the starting point. We start with the detailing, preliminary detailing, even before the analysis is done, or even before the structural design is done, because sizing has pretty much been done at that point. So if the reinforcement, typical reinforcement, most common reinforcement, code-based reinforcement, detailing requirement reinforcement, all the basic rules, rules, experience can do that, then we already have a kind of a working model on which to start the next steps. And we can go on to estimate the preliminary cost estimates, and we can also make the preliminary ones. This is actually done in many offices. And they already have practices. They have previous experience. They can prepare many things based on that. But it doesn't really fit into the BIM workflow yet, because this information hasn't been put by structural engineers into the system. It is just assumed based on some parameters that they might have in spirit. So what we're saying here is that when we do that, then he can update, but then we go to the next level. We update and verify using DTAX or SAVE or whatever software we buy, and then we can go to the final design and final estimate. So we can keep on improving that on one side and using that information on the other side. Then we demonstrate this one through one of our programs that we are developing called CSM Reach Express, and that is based on completely parametric BIM system. That means we define the components of the bridge in advance, complete with the reinforcement details as the starting point. So because we already know what it's going to look like mostly, maybe a few bars may change here and there, but 80-90% will be just following the detailing rules and detailing practices. So we get that in the whole model with the definition and the reinforcement as the object, as a starting object, as a complete object. Once we have that, we can then use that directly to compute the quantities and the costs, because it's already fully defined. You don't need anything else. And we can also determine the capacity of the section of the everything. So the structural capacity is also known, and the cost and BOQ is also known as soon as the component is created or as soon as it's born with the rapid detailing put back into that step, and not just size it, put the reinforcement there, 3D proper into the BIM system. So that's what we are saying. And if I expand that into a full workflow for the bridge, then it can start from the site, from the Google map, you put the bridge there, you gain the parametric model, and then you go to the analysis, you go to the design, we can do all of that workflow, we can calculate the capacity, we get that, we get the section, we get the final reinforcement, we go to Revit or ILC, transfer it to the BIM or with virtual reality, and then you can get the cost estimates, we can get the EOQs and done. And you can then get the final report and then put it back onto the Google map to complete the cycle. But at the same time, you can go and generate the calculations, and you can get the BOQs, software in the middle, and that we have done direct from the objects, like I showed you in the previous slide, that we can see from here that we can, in fact, bypass that workflow, traditional workflow, and directly get this information. So this workflow, together with the opportunity to do this early on, gives this program to be used at preliminary design or preliminary planning in as good a manner as it will be in the end. So this is what we can also do for buildings. We can have the building architectural design, create a Revit model or a thing, and from there use an IFC inverter and do the detailing right away without going to the structural design at this point, because we know typical detailing rules already from codes and practice. And then this information can go to contractor, architects, officials, project managers, or structural engineers. And then later we can go to ETAPs or other programs, create the model, verify it, come back, update the same model, and then revise. that is the advantage of BIM, because we can update very quickly, automatically, in most cases, and that takes minimal effort rather than changing everything by hand one by one. So this workflow using the detailing then can give the opportunity to do things earlier on and to reduce the difference between the final and the preliminary design. So this is the workflow using the traditional way, using from building to when this is a credit model, for example, we can get the structure model, we get the index model, we get the analysis model, we get the analysis results, we get the BC ratios or reinforcement from there, we get and then in the detailer, key tabs can generate all the rebar, the reinforcement, details and the cage, and we get the full rebar model generated 3D from the information from the design, and that is part of the heat tabs detailer. And then we get the drawings from there and sections, we can cut from there, and then we can transfer it back into the web using cross-Revit, and then back to the BIM model. So the cycle can now be completed in this way. This is the traditional kind of a way that we can. So this is one work. What he's suggesting is an alternate workflow so this is cross-Revit, and that is Autodesk that can complete this whole information. That's many people are using that already. Now, the alternate is that you go from that and then get that structural model and to do the detailing right away. Don't go to model and analysis and design yet. And based on the detailing rules, so we can activate the detailer or detailing system in such a way that it directly gets the BIM structural model, which already has the sizes in it, and puts the reinforcement there, and then you can bring it back, and then the reinforcement, many clashes, many issues can be resolved at that time. And then second workflow is that we can go back to ETABS, and the parallel workflow is we go back to ETABS and move that and update the model and make the changes wherever it's done, and then update the Revit from there also. So this workflow gives us the opportunity to have an alternate, faster workflow and more efficient in many ways, because not a benefit can be drawn from this detailing as the primary starting information for a BIM. So to conclude, the key takeaways that we can move is that the structural engineers need to increase their engagement and adoption of BIM. I think that as a structural engineer, I must admit that we are probably not as much engaged as many other disciplines are, and we need to be more. Of course, it depends on various companies and more, but I'm talking in general of the engineering practice. The design workflow can be improved if structural BIM is prepared earlier on in the life cycle. So as we can see, there's a lot of benefit to doing that. So the structural information model or structural detailing could be worked on earlier, because even for structural engineers, if we have the detailing, we can do performance-based evaluation, we can do capacity-based design, we can do many things that require the reinforcement to be defined first. So that can also facilitate that part. Then the overall project lifecycle management can benefit more from the BIM. The structure is used as core, because that's ultimately what will be built first, as we have seen, that without that, nothing else can be built. So why don't we create the model also first, rather than delay it until the later we will be what first it is. And more lifecycle phases specific to structural performance, resilience, and sustainability can be integrated into the BIM process, as I showed you. LiDAR scans, structural monitoring, and AI now, of course, we can't know that. All of those things can also be added to the whole workflow if the structural information is more comprehensively integrated and included in the BIM systems and workflows. So that's what I just want to share with you, and I hope that this information can be useful. Thank you.